Hi, my name is Scott Simpson, and today we're going to continue our discussion of the harmonic oscillator. So in the previous video, we determined what the what the potential would look like for this type of system, a system trapped in a harmonic well or behaving like a harmonic oscillator. And we arrived at this applying the Schrodinger equation, where this portion was the result of our kinetic energy, this portion was the result of our potential. However, we have not actually solved this equation. We haven't developed any wave functions. So the portion of this talk will be about, first, what is this K, and then how this force constant, so what is that value? And then eventually we'll be looking at how to manipulate this equation to solve for it as a differential equation. So let's get into it. So the first question we're going to ask is what is the value of K? So that constant that's right there, what is it actually? And it comes from classical mechanics, or at least we have to go back to classical mechanics. It's probably the easiest spot to think about it. So a lot of times in classical mechanics or classical physics, you're taught about a pendulum swinging back and forth. So from classical physics or mechanics, the position of the oscillator versus time is given with the following expression. X of t is equal to x sub 0 sine square root k over reduced mass times t times this phi portion. Where this x naught is the amplitude, or the maximum amplitude of the oscillation. K, that's our desired force constant. That's the thing we want to figure out in a minute. M is our mass. T, of course, is time. And this phi is a phase factor. Okay, so that's not the most important aspect to what's going on here. This you can get out of classical physics, but we still haven't gotten a value for that K yet. So if we consider how much time it takes for this oscillator to complete a cycle, so basically go back and forth, oh, excuse me, back and forth once, we're gonna look at that oscillation time as tau. So it takes the oscillator tau seconds to finish a cycle. The frequency of this displacement then so we'll use nu as our frequency because we always do that. That would be equivalent to 1 over tau. In this case, if you plug in and you solve for tau, what you end up getting, or at least for the frequency, is that as the expression. So 1 over 2 pi square root force constant divided by the mass. If we solve for K, we can do that. So we're trying to move things over. So let's just start with our expression. We'll get rid of tau because it's just kind of an intermediate. Let's move this 2 pi over. Now we need to move that square over. So we get 4 pi squared frequency squared is equal to k divided by m. Then we can do 4 pi squared frequency squared mass is equal to the k. Okay, so now we have a value for this force constant, and that's what the value of the force constant is in the harmonic oscillator. Next, what we are going to do is we are going to take that and we are going to plug it into our equation here, and then we're going to try to solve a difference.